Newton's law of cooling is given by this equation right here. So T, this is the temperature after a certain amount of time, lowercase t. Yes, it's a lot of t's going on, but just follow along. So this t is how much time has elapsed since something started to cool. A is a constant. E is our favorite now, next to pi, transcendental number. K is a constant, and then t is another time. So this is how much time since something started to cool. And then T sub S, this is the environment in which it's cooling, whatever temperature it's being exposed to. So my example here is we have a cheesecake taken from an oven at an ideal internal temp of 165 Fahrenheit. For all of my cookers out there, that is accurate. And it's placed in a 35-degree refrigerator, which is a bit cooler than most, but this would be then the outside temperature, or the temperature that the cheesecake is being exposed to. After 10 minutes, we record that the internal temperature is now 150 degrees. If you must wait until 70 degrees to eat, because we want a cheesecake that firms up and actually stays together, how long will you wait? This is the question we're looking at, and this is why we're going to use logarithms and exponents, because the variable I'm looking for is time. How long will it take to get through there? So we know 2 points. The first point that we know is at time 0, I have 165 degrees, so I'm going to write my equation with that in mind. So I have T sub 0 is equal to A times E to the K times 0, because I said my time is 0. That's a K. Just trust me. It's a really messy one. Plus the outside temperature, which is T sub S. But I know the temperature at time 0 because I'm told that when I take it out, my cheesecake is 165 degrees. Work this backwards. Oh, and TS, I know that too. Why did I not write that down? My TS is 35 degrees. Subtract 35 from both sides. I get 130 degrees is equal to A times E to the 0 power. K times 0 is 0. E to the 0 power is 1. So A is 130. That's my constant for this function. Utilizing that now in my equation, I rewrite my equation substituting the A with the 130, but then I have another data point because I know that at 10 minutes in, it's 150 degrees. So I'm going to put those numbers into my equation and work my way through. So now I have 150 degrees is equal to 130 e to the K times 10, because I'm 10 minutes in, plus 35. Subtract 35 from both sides. I have 115 equals 130 e to the 10K. Divide both sides by 130, and all of e to the 10K equals 0.8846. I now have a base E. I want to convert this into a logarithm, so I'm going to do it one of two ways. First way I'm going to do it is I'm going to say, well, I'm going to take the natural log of both sides. So what I'm going to do is I'm going to, on the left-hand side, I'm going to take the natural log of 0.8846 equals the natural log of E to the 10K. Using my principles and properties of logarithms, I know that the exponent on the right-hand side comes out in front, 10K times the natural log of E, which is 1. So I'm left with, on the right-hand side, 10K. And on the left-hand side, I'll just leave this for you to figure out later on, but it's the natural log of 0.8846. It's a number. To solve for K, I divide by 10. I divide this by 10, and I will find my value for K. So the value for K that we got was negative 0.0123. I now have my full equation with all of my constants in here. So now I have the cooling formula and equation for a cheesecake that had an initial internal temperature of 165 in an outside temperature refrigerator of 35 degrees. The question then asks, how long until it's 70 degrees? So then I substitute the final temperature as 70, and I work my way backwards the same way I've been doing it all these other times to find the final time. 35 equals 130 e to the negative 0.0123t. I'll have 35 over 130 equals e to the negative 0.0123t. Like I did on the other one, I'm going to take the natural log of both sides. I am left with so left side is natural log, and we'll figure that out later with a calculator, equals negative 0.0123t times the natural log of e, which we said already we know is 1. Divide both sides by negative 0.0123. Divide this whole thing by negative 0.0123. And I can finally find that the total time to temperature down to 70 degrees is some number that you'll find when you plug it into your calculator. And as I've alluded to before, here are your properties of logarithms. If I have same base and I'm adding, then when I'm putting them together, they're multiplied. And it goes backwards the other way, as I give it as an example. Log of 200 is equal to the log of 100 plus log of 2. How do I know that? Well, because 100 times 2 was the 200. So sometimes we'll use it to go directly into the multiplying. Sometimes we'll have multiplying and work it backwards out. And then log base, or log of 100 is 2. So log base 10 of 100. So 10 to what power is 100? That's 2. And then log of 2, that's 10 to what power is 2? That's not an easy one to figure out in your head. I show that because as you get to some more challenging problems, you might have something like this and have to then realize, oh, wait, 2 can be rewritten as a log base 10 of 100. All right. Again, that would be a considerable challenge that I would be expecting. Moving on. So that's the first property. That's the multiplication and addition property of logarithms. We have the division and subtraction property of logarithms. If I have two logarithms and I'm dividing, like over here, and let me rewrite this. This should be rewritten as log of a over b. That's how it should be, not log a over log b. Log a over b is equal to the log of a minus log of b. All right, I did not give another example like I did with the multiplying, but it's that principle. If I have two things, so we'll see in a lot of problems that we'll have some type of a polynomial in the numerator, maybe a polynomial in the denominator, and then we would split it up by doing it by subtraction, where they can take the numerator to subtract the denominator one, and then we'd have the log of just one polynomial in some type of an equation I'd be working through to solve it for some value. A times log of b is log b to the a, or vice versa, what I did in the earlier problem. When I have an exponent on something I'm taking the logarithm of, the exponent comes out in front. If it starts out in front, I can work it back in. I can do it in either direction, and the problem will dictate which way you have to go. And the last one here is the change of base formula. So if I have log base b of some number that's not 10 or not e, I can change this as long as these two have the same base. So log base b of a will equal log base c of a over log base over, I wrote this down wrong, folks. Much like you, I get in a hurry sometimes. And it's not capital B, it's the lowercase b. So whatever this is, I take log base, whatever I'm having. Usually it's going to be 10. We're going to say log of a over log of b, the base. That's how I could change out of one base. There are some things that do occur that aren't base 10 and aren't base e. They might be base 5. So I don't have a base 5 on a lot of calculators for doing that, or a lot of people don't think in base 5. So I can convert it into base 10 in that last one by doing the log base 10 of what I'm taking the log of, divided by log base b, whatever the base was of the original. And you can do it the other direction. It doesn't often happen where I start here and end here. It usually starts here and ends there. So those are your properties and principles of logarithms. Yeah, that's probably enough for today.